So I'm going to talk about 4 points that I am keen to tell you about. First, the progress of ITER, and tell you about, yes, the progress in the schedule. I would like to have some perspective about some of the history of this project, because now that we are back on track, I think many of you may have some questions about why we got ITER in the first place, like the way it is, and then also try to give you an outlook on how ITER could be useful today. So now when I was here, well, I wasn't here. When I was in London at the Fusion Energy Conference 2 years ago, situation was not as good as it is now, not even close. I mean, we had very difficult problems with of repair that we had to deal. We had problem with the regulator. We had to deal with a schedule that was hardly ever kept in this project. And I think that in as much as you are disappointed of that, I was also very disappointed. So it was a challenge for us to try to deal with these problems, and I will show you that I think now these problems are, say, under control. So first on the repair. You remember 2 years ago, maybe you don't, but 2 years ago we had some issues of repair of the vacuum vessel and also of the thermal shield. And we transparently communicated to the community all the technical details about these issues, because we are really keen to make sure that nobody else will do mistakes as such. So we have now set up essentially a workshop at ITER site, and we have progressed with the repair of the bevels to build up some, by TIG welding, build up the bevels. But this is not that simple. It had to be also, of course, machined and tested, and we also had to deal with the questions from the regulator, but all of that is okay. And in as much as okay is also has been the repair of the thermal shield, where we had to remove all the pipes from the thermal shield, the cooling pipes, and proceed with the removal of some materials to avoid that there would be any residue of stress corrosion, and pipes rewelded and repolished to have the level of emissivity that we wanted to achieve. Likewise, on the central solenoid, we achieved pretty good progress. Now we have all the 6 modules delivered from General Atomics, except the spare one that will come shortly. 5 are stacked. I think the 5th was stacked last week. And now we will proceed with assembly of the full system, say the pre-assembly of the full system. All TF coils are on site, and you see 2 of them on the appending tools, which are used to put the coils in a vertical position before the pre-assembly of the sector modules. All the PF coils have been fabricated. Here, the last one fabricated in the middle of last year. So this had to be fabricated on site, could not be transported, so except the 2 small PF1 and PF6 who could be transported, all the other coils had to be, all the other PF coils had to be fabricated. And likewise for the error field correction coils, where we have 6 that are installed, and then we have the other 12 are either completed or already on site. The vacuum vessel sector, which has been a big concern in terms of delivery, and where we have a lot of lessons learned that we will have to compile and communicate. We have all the 4 sectors from Korea. 2 are already in the pit, as I will show you, repaired and back in the pit. And we have, say, 1 now on the assembly frame, 1 under repair. And we have, say, 2 sectors from Europe and 3 more to come that should come during the course of next year. Of course, we are following very closely the progress on that. We have progress on many, many fronts. I don't have time today to show you all the image that would pay tribute to all the work that pretty much all of you are working on this project. But a few highlight, again, is on the divertor cassettes. Production is ongoing. The qualification phase for all high flux components is completed, and the serial production is well underway. So that is going to be an activity that we will have to follow closely, because we will plan now with a new baseline to install the divertor at the beginning. So how we stay now with the sector module? When I came at the Fusion Energy Conference 2 years ago, we had to remove 1 sector module to repair it. And so in the meantime, we have removed it, we have dismantled it, we have repaired it, and we have put it inside, again, the machine. And so did we with the second one. Now, to give you things in perspective, I will show you a little movie of a very interesting moment, which is when we put the sector module, we lift the sector module from the assembly frames onto the pit. Okay, we have now an execution rate on the sector module pre-assembly, which takes between 5 and 6 months. Take into account that the first sector module took about 18 months. So the first one that we have to repair, while this one, sector module 6 and 7, took about 6 months each. And we are trying to go even faster. The result is that sector module 6 that was installed, say, in the middle of the year before the ITER Council was done, so compared with the baseline, about 7 weeks ahead of schedule. So very proud of that. Now, we have now 2 sector modules in the assembly hall, which are being, say, prepared. One of them is the sector module 5, the first one from Europe, which we plan to install probably early December. Again, it should be several weeks, probably 6-7 weeks ahead of schedule. And then the third Korean sector module, sector 8, that will follow immediately after. But what is very important for us are the odd 1, 3, 5, 7, and 9, total 9 sector modules, because that is on the critical path. So, critical path now on this assembly is between 6 to 7 weeks ahead of schedule. So, and we want to keep it like that. So not enough time, again, to tell you all what is going on, but also on other fronts we are making progress, apart from very large progress on the plant systems that I will not have the time to explain about. We have now progress on the assembly and later in commissioning of electron cyclotron system. This is one of the first gyrotrons that we have now installed, and now the magnet has been energized. We have progress also on the neutral beams, where Mythica, we have 2 facilities for ITER. Of course, we will also benefit from all the work being done at ASIP, but say we have 2 facilities to reach 1 megavolt. We have Mythica and Spider. There will be a dedicated talk, by the way, on Wednesday on this topic, where on Mythica we have now had to contend with some issues in terms of voltage holding of the source itself that would normally operate at -1 megavolt. A screen has been designed and installed. Another projection is that we should be close to achieve, say, 900 kilovolt, say when we extrapolate the electric fields that we have to the full 5 stages. So that is going okay, although, say, we would like to accelerate to make sure that we will have this heating system in time for operation during, say, the SRO. Likewise, for the ion source, there is good progress in achieving on this full-scale, say, ion source, the full current density that we will need. Okay, on magnet power converters, we have multiple stages. Stage 1, which will be, say, the essential one, it's completed, and commissioning, installation is completed, and commissioning of the individual systems is well underway. We will have also stage 2 power converters that will be, we have placed a number of contracts, and we have a number of new power supplies that are being, say, the contract of which is being prepared now and signed now for example, the ELM power supplies, which are IGBT type of converters, as opposed to thyristor power converters for all the 18 ELM power, coils. The cryogenic plant is now commissioning, it's completed, and we started in December helium liquefaction. It's a little bit early, let's say, for ITER as such, but we will need finally this helium for the test facilities. So this is a picture that I took just last week. This vessel was actually constructed here in China and at record time, and we decided to install this test facility pretty much at the end of 22. It's regrettable that the project decided not to test all coils, I must say that, but at least we will test, we expect 4 coils. And so that is the cryostat, and it will be very useful, I believe, also to set up some infrastructure for testing of coils from other facilities. So I want to spend a few words to thank the community for having supported the definition of the ITER research plan in accordance with the new baseline. The research and technical baseline documents have been thoroughly revised. I don't have much time to spend on this. Of course, the main thing in the baseline was the reordering of things and plans. But for me, it was very, very important to see so much work from all of you, from all the research community to make this important document, now completed. But, you know, I know also that there are a lot of experiments that need to engage to further validate our integrated modeling tools. So thank you for doing that. On the DMS, a few words on that as well. The DMS has been, foreseen now for over a decade. The first, it was, a massive gas injection system that later evolved because we were aware that we could not get the valves, performing enough close to the plasma to shut down reliably the plasma itself. So that's why the shutter pellet injection system was, conceived. And this is a work that was done by the community at large. You know, the task force, the DMS task force that was led so well by Mikael Lennon, that unfortunately we lost last year. And I think that what the task force achieved together with the team in IO on such a short time scale is quite amazing. So the original DMS was mainly focused on the control of thermal loads and electromagnetic loads. So what would happen, for example, in the case of a VDE? And the problem of runaway electrons was, from my perspective, or from the perspective of many, maybe put a little bit under the carpet. But we know well we can expect what runaway electrons will do in a machine. And so part of this logic has been behind the rebaselining itself, the concept of sequencing of the project itself. So the most important point for me to make is that our new baseline is a radical improvement because it allows a full commissioning of the machine before we will move to tritium operation to gain experience with the DMS as on what we will install as a sort of sacrificial wall. So we will not put the water-cooled blanket from the beginning, the water-cooled first wall. We'll put, a first wall that will be able to operate up to full magnetic energy for a reasonable duration. Of course, we will need to put all the heating, as much heating as possible. Who knows, maybe we will even get in H mode. But important will be to make sure that the machine can be commissioned and disruption can be controlled before we will move to DT operation, at which point in time you are all aware that repair will be much more difficult to achieve. So now, before moving to some data about the project, I thought this time to give you some, some perspective of questions that I frequently get. And I'm very surprised by the questions I get from sometimes scientists and frequently from even politicians. So they come to ITER and say, oh, wow, what an engineering marvel. Thank you for going so fast. Thank you for taking this project ahead. But why is it so big? Why? Why is it so big when there are so many, that around the world that say that they can do things much smaller? So I have to contend with the issue of explaining that point. And I should tell you what I think is the fact of the matter. Because many of you don't know maybe why ITER was decided to be so big. First is to get the current. We need 15 megampere. I remember very well the community insisting first on ignition that would have required, to be conservative, in excess of 20 megampere. And finally, to make sure that to get the triple product that we want, we need 15 megampere. I remember this very well, at this aspect ratio. So, okay, that's what drove a lot of the machine design. Secondly, we need to have a certain distance between the plasma and the magnet. And this is not a question of superconductor, high temperature superconductor. It's a question that was driven by shielding on one side, insulation damage, et cetera, et cetera, et cetera. But also in order to make sure that we would test the machine and we size the machine so that breathing could be achieved also in the inboard. And I remind you that at this point in time, dimensions are such that if we want to have any, chance to succeed, to have sufficient breathing ratio, we need in excess of 1 meter between the plasma and the TF coils. So when you put a meter between the plasma and the TF coil, you will need to increase the major radius by 2 meters. This is for a given plasma current. This is simply the fact of the matter. So, and the question that I get next is, but what would it be if we would design it today? Would it be different? And, you know, I have been in the design team more than 20 years ago, and I looked again at all the nodes and how we did the system code analysis, and I tell you, in my opinion, not so much. Maybe 20, 30 centimeter. Maybe we could use some of the know-how that was developed during the fabrication that we are also trying to communicate to the private sector. First, this question about the field. I hear frequently that the problem is that now that we have, the fact that we have high temperature superconductor would allow us to make ITER much smaller. I don't think so. Take into account that in the ITER cross-section, niobium-13 take only 4% of the cross-section. And niobium-13 can operate at higher field. It does not constrain at 12.5 Tesla. Only 4% of the cross-section is niobium-13. And the optimization was not driven by some cliff edge effect of niobium-13. Of course, it would be different with niobium-titanium. The work was done early in the EDAs to optimize the magnetic field. And when you put sufficient shielding, increasing the magnetic field, there is a problem of power flux, of course, that goes in the wrong direction. But there is a problem also of, let's say, controllability of the plasma itself. Different story would be if we would have no shielding. In this case, I completely agree that a burning plasma experiment that would operate for a short time, no problem. We can have, and we have the advantage to operate at much higher field. But it's a question about power flux for a short time. So this point was not invented recently. This was discussed also in the 80s. In the 80s and the 90s, we had projects like BPX, CIT, and FIRE, which operated okay, and the current didn't reach 15 megampere. But say BPX that had 12 megampere had a triple product, extrapolated triple product that was not so far from ITER, a little bit different maybe with FIRE. But the key thing was that they were short pulse. So they could not operate for a long pulse because, one, the power flux on the diverter was too high, and two, the question about, yes, the shielding. So this I mentioned, and I will leave it in the view graph for others. And I show also what happened in the late 90s, early 2000s, when different options for ITER. And if I may, if I would go back in the design of ITER, probably I would suggest to reduce a little bit the magnetic field, because that would yield to major simplification in some of the engineering interfaces, which drive the cost much more than we think. It's not simply size that drive the cost in a Tokamak. So the last question is, well, the third question is about the cost itself, as I said. This we will try to address. The question about the ITER cost is a major problem. The ITER cost has been way too high, and we have to find the reasons behind that, and we have to find, and I am convinced that we could design ITER, we could build ITER for a fraction of the cost it has actually costed. There are a number of reasons in terms of the sharing, in terms of the politics around this project, and some of design solutions that have been, say, over-costly. And we will have to address that. Even though now we are, I would say, on a much better time frame of execution, we still have to address that. Because the question, I don't think it's so much from fusion whether we can get more energy than the energy we put in. The big question is, will we ever be able to get more money than the money we put in? We see so much complexity in our technology that we have to address it from my standpoint to reduce such complexity in such a way to reduce the unit cost to acceptable level. And I want to mention also this question about what are the remaining challenges that we have in fusion, because at this conference and also what happened before at the Fusion Energy Group, there is a lot of hype, there is a lot of expectation, but hype will not solve our problems. And so I'm very glad that the community is aware of that, and we should remind ourselves all the big challenges that we will have. Say, speaking before about tritium breeding, I was trying to look whether today we have a design on tritium breeding that we would fit in the ITER size, which, by the way, is quite generous. It's about 1.2 meters. Say, would we be able to achieve in ITER a breeding ratio in excess of 1, and I don't think so. We are not there. We don't have a design of the breeding blanket that would be able to sustain the power flux of ITER. So let alone what will happen next. So we have to solve this problem head-on, and I don't think this problem will get solved by itself. There is the question of power flux. We still have a situation, I remember 30 years ago when I started working in ITER, that I was told power flux will be solved, and we still have a situation where when we look at the ratio between power flux in the divertor and the average power flux on the first wall, about a factor of 100. So you can understand how serious this problem is, and I think it's still to be solved, because at this level of power flux, there is no design of a first wall that we can cope, let alone the divertor. The first wall in ITER is now all included, having to work at a power in some region of 2, 3, even 5 megawatt per square meter, when the average power flux is about 0.5 megawatt per square meter. So how can we, say, have a cost-effective technology that breed the tritium is a very big question. So very important to develop scenarios that have been long-lasting, and long-lasting has been the expectation that these scenarios would be developed. So now I come to tell you a bit about the project and how to make ITER useful now. So ITER is not my project, it's not their project, it's your project. This is something that belongs to the community. Our job is to make it go faster. And thank you for going so fast, Yangang, so that we also have some competition. So we have to get this done, and thank you, by the way, to the great contribution that we get from China in ITER. But ITER is, from my standpoint, should be useful now. So we have this fusion, say, knowledge transfer project. So we are working on that. And we think that for the community, it's also a training ground. It's not a place where you go and end your career. It's a place where you can learn. So to come to the end of my talk, we had restructured the organization in 2023. We have recovered the trust with our regulator. This was very important. We have reformulated and restructured most of our assembly contracts to be able to move at the pace that this project deserves. We have repaired the components, we have developed a new baseline, and we have, say, worked around the project and design control processes to move fast and reduce the open PCRs and whatnot that we are driving the cost up. So now in 2024 and 2025, I'm pleased to tell you, 2 years after my last intervention at the Fusion Energy Conference, the scheduled performance index in ITER is 1.01. This is the last number I got last week. And the cost performance against the new baseline is also in the green at 1.14. So one may think, okay, we got this because we just put the schedule in a more diluted way. This is not the case. This is actual financial data, okay? So with an SPI of 1.01, in 2024, we have achieved 35% more work than in any previous year, and 2025, we will increase this even further. So I come to the end of my talk, okay, just in time, SPI of 1, and then leave this slide, this video in the background for those of you who haven't seen ITER. Please come and visit. Thank you.
Thank you very much for your talk. Now we have time for one short question.
Yeah, I'm very much impressed by your honesty as a very talented engineers. And many of the fusion people say it's kind of dreams, but some of my colleagues say that we have to be honest to say the truth. So in that sense, you bring us a lot of important issues we should face in the futures. And I greatly appreciate this has to be for everybody, including Jiangang Li. Yeah, thank you so much. It's just a comment.
Thank you, and I would like to say that I really appreciate your comment. For our community, we have now, say, a community, a civilization that is hungry of energy sources. But we have to give the right perspective. We have to make sure that the expectations are aligned. Otherwise, we will be in trouble, by the way. If we are not honest, there will be a time where we will be in trouble because we may not be able to deliver. So we have to address head-on I think we have courage, and we know how to solve problems, and we have now the political support. And if we are honest, I believe that we will succeed. So thank you, Kikuchi-san, for making this very clear from your side.
Thank you. We could have some time for the last question for this. Yes.
Evgen Kazakov, Belgium. Thank you very much, Pietro, and congratulations to you and the ITER team for this encouraging progress. We all are very happy to see it. My question is very short and related to the coil testing, which you mentioned. What will be the criterion for those 4 coils, TF coils, out of 18 for the tests?
So I think what I would have liked, of course, is to test all coil as we did in JT60SA, where we tested all the spares and everything, and nothing would be assembled without testing. Unfortunately, this cannot be done. I mean, we would delay the project tremendously. And I think that what at least we can do is to see if there are systematic issues that then we can check, mainly the joints, and then to make sure that they are patient-tight. You know, we want the plasma to get inside the vessel and not inside the cryostat. If we get the plasma there, it's bad news. So there are a number of things that I think we can describe in detail, I can tell you in detail, that we can do, even though we will try to operate, we will not be able to go at full current. Not at full current, I can explain you, not because I'm afraid of going to full current, but it's because going at reduced current, about 50%, we will be able to keep the discharge voltage to a low level so that we don't need to have all the connection to be patient-tight. So this is so that the discharge voltage for a single coil operation will be low enough. So I think there is a lot of learning that we can do on the 4 coils plus 1 spare and on PF1. It will prepare also for the commissioning. I'm sure we will pay this test facility, say all the cost of this test facility 3-4 times by doing this and then being able to accelerate the commissioning itself. So thank you again, and I can say this. This is really me thanking you, because I know how much the community has contributed. This is the ITER project, is all of you. It's not, you know, some special place on earth. This is really, the community that contributes, and all the companies, not only the research institute, all the companies that provide tremendous value to ITER. Thank you for doing that. I really appreciate.
Thank you. Let's thank our 2 speakers again.